we're doing some optimization problems here. So let's take a look at this one here. This is a classic fencing kind of issue where we're trying to maximize the area. We have 600 feet of fencing, and we're making a corral, which is rectangular but with a semicircle on the end. So a nice little twist here. And as always with a lot of these optimization problems, well, all of them, you're trying to optimize something. You're trying to maximize or minimize something. In this case, I'm trying to maximize the area. So I want to make sure that that is the thing I have an equation for. I need an equation for the area, if that's what I'm trying to maximize, because I know how to find maxes and mins, using calculus. But I need an equation to, perform some calculus on, get the derivative, set it equal to 0, all that good stuff. So I gotta go through my work here and see what I got. So where do we start? Let's label this diagram with some variables here. And you've got a rectangle, a semicircle. A semicircle, the area of it is half of pi r squared. So I think I'm going to start there with calling this radius something. You can call it r, x, whatever you like. But whatever this radius is, the side of that rectangle on the bottom there is going to be twice that radius. So I can call that side 2r. Now this is not a square, so the other dimension here on the width or the height of this rectangle is just some other variable, y or w, h, whatever you like. But at least I have some variables in place now. So describing the area of this region, it's going to be the area of that rectangle, which will be base times height, or 2r times y, plus the area of that semicircle, which is 1/2 of pi r squared. Okay, so I've got an equation, and it's got two variables in it like a lot of these problems end up having, so there's always some secondary condition they give you which allows you to solve for one variable and substitute that in. And in this case, I would say that is the fact that there is 600 feet of fencing. So that refers to this perimeter, or of this figure. And so our total perimeter can be 600. So I just got to make an equation for that perimeter. And you've got the sides here of 2r plus 2y plus this curved portion from the semicircle. So that is half of the circumference. And so half of the circumference is 2 pi r. So half of that would be pi r. So that would be the distance around that semicircle. So I'm going to include that in my perimeter equation here. So you have 600 equals 2r plus 2y plus pi r. And now we're just going to solve for one of those variables, substitute it into my area. It really doesn't matter which one, it's just whatever one seems easier. To me, it seems easier to solve for this y. So I'm going to subtract, isolate this. So subtract 2r, subtract pi r, and then I'm going to divide the whole thing by 2 to solve for that y. Up to you whether you want to leave it as a big fraction or if you want to break it up. Maybe breaking it up would actually work out nicely, because that's going to be 300. 2r divided by 2 is minus r. You're going to have minus pi over 2r here. But still, seems nicer than using that whole big fraction, I think. So now I'm going to take this, and I'm going to substitute it in for y into my area equation. Okay, so we've got area equals 2r times, and y, as we just said, is 300 minus r minus pi over 2r. That's y, and then we still have this plus 1/2 pi r squared. So that whole thing is now in terms of r. Area is in terms of r, and that's what you want. So this is really where you're kind of left to your own options of how do you find that derivative. you know how to do the derivative of just about anything at this stage of the game. It's just a matter of how complicated it is with product rules and chain rules and things. This wouldn't really be too bad. It would just distributing, simplify. But I think I'm going to, well, I think no matter what, I think I'm going to distribute this and simplify the equation a little bit. So if I distribute that 2r, you'll have 600r minus 2r squared. When I distribute 2r to pi over 2r, the 2's will cancel, but I'll be left with minus pi r squared plus 1/2 pi r squared. And even those two things right there, those are like terms. You could simplify a little bit more here. So I'll have 600r minus 2r squared, and negative pi plus 1/2 pi will be negative pi over 2r squared. Okay, so now you got something. The derivative would actually be very easy. Just do the power rule here, pretty straightforward. And that's probably what I would do, to be honest. I would just be in the groove and go with it. But since we're on a video here, I'm going to also take this opportunity to show you how to use the calculator to find those critical numbers by graphing the derivative. So this is a nice little time here. And if you want to do this, and this kind of goes for the AP exam and how it goes in my class too, you can use your calculator to find things like that, but you have to represent with notation what it is you're doing. And so just think what you would be doing if you were doing this all by hand. I would be finding when is a prime, the derivative, equal to 0. And it would be for what r value. That's what you're going to use the calculator to solve. Right? Maybe it'll be a nice value, maybe it'll be an approximation, who knows. But you see, I've at least communicated. I can't just have the big thing on the AP is you can't just have a number appear out of nowhere without expressing what it was the solution to. And hey, this is enough communication right here. Derivative equals 0, boom. Okay, so now let's bring up the calculator here. So we've got this, and what I'm going to do is I'm going to imagine that this a equation was just something that was crazy ugly to get the derivative of. So I'm going to put that in y equals. So 600, and you use x when you're graphing, right? 600x minus 2x squared minus pi over 2 x squared. Okay, so there's that equation. If you want to take a look at it, go ahead. But I'm going to jump right to the derivative. And so the derivative here, your calculator can't give you the derivative equation, but it can sketch the graph of the derivative by using that Math 8 n derivative feature. So in y2, I'm going to hit Math, and I'm going to scroll down, or you can press 8, because there it is, n derivative, and here's we go with the notation. Maybe it's been a while. We're taking the derivative with respect to x of, now you can either retype that equation from y1, or remember there are little shortcuts in the F4 menu. So alpha trace brings up this, and you can just hit y1, and that way it knows you're using the equation that's in y1. And here's where you would tell it what x value you want the derivative at. Like if you wanted the f prime of 2, you would put 2 here, and it would spit out that one single value. But I want to see the derivative for all x values. So I actually put x equals x. Okay, now if you hit graph, you're probably not going to see much. You're going to see that blue vertical line here, because keep in mind the kinds of numbers you're using here. You're talking about the area in terms of r, and that r is your radius. You have 600 feet of fencing. The radius could be pretty big. Now it wouldn't be up to 600 because, think about those dimensions you've got to use here. Right? You got 2r on the bottom there. So I would say the biggest your radius could possibly be is, 100, 150 certainly. If your radius was 150, that bottom piece would be 300 already. Then you wouldn't really have much left to use for the other sides. So I'm going to adjust my window here. My x is, my r, my radius. So like I said, I'm going to go out to 150. for my x max. Now, if you are only graphing the derivative, which is what I'm really looking for, is where does the derivative equal 0? This is what's nice, because then you can always kind of just home in on the x-axis. That's what you're looking for, the derivative equaling. So you can always kind of have your y min and y max be at -1 to 1, just to kind of zoom in on that x-axis. The x values might differ depending on the problem. And I'm actually going to go to y equals, and I'm actually going to shut off the first graph, just so it's not even there to distract me, and only graph the derivative. And the nice thing about during this unit, you can leave this set up in y2, and for every problem, if you change y1, it'll change right along with it. So you can kind of leave that there. So now let's just see. I'm going to hit graph, and we're going to see if I see anything. Okay, well, I definitely see that red graph. That's the derivative graph. You can hit trace, and you can see at x equals 70, it's at positive 100. And it's changing so dramatically. Now it went into the negative territory, somewhere between there. Look at that, negative 29, 83, it's at positive 4, and then it's into the negative territory. So remember, what we're looking for is a maximum. So, you know, our graphing unit, I should be saying, when is my derivative changing from positive to negative? That would be a relative maximum. And sometimes, you know, this window, if you really want to see it better, you can change that to negative 0.1 and 0.1. Maybe it won't even appear quite so vertical, but it's still, it's changing so dramatically. But all that matters is you know that it goes from positive to negative. We just did that. And it's right around 80, 83, I think it was. So here's the thing. I'm going to hit second trace, because I'm going to calculate the zeros on this. So item 2, 0, left bound. Now it was right around 83 or so. So you just want it to be some x value to the left of that. Right now it's at 70. Sounds good. Hit enter. See, and it set that little left boundary. Now the right bound, you definitely want to either push it, or if you kind of remember that, hey, look, I'm just going to type a value of 100. I know it was before 100. And now it sets that right boundary. Your 0 is somewhere in the middle there. The guess doesn't really matter. Just hit enter, and it should go to the 0. And there it is, 84.014873. Now, remember, you have to be accurate to 3 decimal places on the AP. So I'm just going to bring this back up here. So I'm going to certainly jot down 84.015. I like to round. You could also truncate, remember, for my radius value. 84.015. That's the radius at which this area of the whole thing will be a maximum. And remember, you want to verify that with some kind of number line or a statement saying that the derivative is changing from positive to negative. And so I'm going to keep doing what I've been doing here. You know, in the previous unit, it's a nice, you know, kind of a follow-up to what we were doing last unit. And you don't have to actually test, because you saw the graph. The graph before that, the derivative was positive, and after that, the derivative was negative, which is telling you the area is changing from increasing to decreasing. You're dealing with a relative max, which is what you wanted. But okay, so you want the dimensions, though, of this corral. So you want to find the width and the height. So just remember here, if you're going to use that value, 84.014, etc., you don't really want to use a rounded value, because that might affect the accuracy of the other numbers when you go plug it into something. So here's some other little tricks with your calculator that in the second half of the year we use more and more as we bring in the calculator use. When you hit second answer, so second negative symbol, I'm going for the answer there. It's the last thing you calculated. And if you hit enter, if you want to see it, it's that value. It's the 0. It's the last thing my calculator calculated. If you want to store this, that way you don't lose any accuracy, there's the store feature right here. So I'm going to store this value in any any of these letters, you see A, B, C, D, E, they're in green on my screen here. I'm going to store it in A. And now, anytime I hit A, the calculator is going to use that full decimal value. And these are just little shortcuts, little nice tricks. They're not essential to doing things, but it's a way to have the calculator help you do what you want to do in the most efficient way sometimes. So okay, so here is how I'm going to play this here. The dimensions of the corral is what I'm looking for. The dimensions is what they ask for. Sometimes they'll say what is the maximum area. The dimensions are, I guess that base was 2R. So on your calculator you can just hit 2A. And it gives you this, and now you can round that, but you know that that is going to be accurate to 3 places. So 168.030, and this was feet in this problem. And the other dimension was y, I guess. So y, and what was y? Y is 300 minus r minus pi over 2r. So this is really where this is kind of nice. I'm going to type just right on my calculator, 300 minus a, minus that r value, minus a minus pi over 2a. And remember, when you order of operations, that a is coming after the fraction pi over 2. If you wanted it in your denominator with the 2, you'd have to put parentheses around it, or use your fraction button. So here we go, and there's the y value. Actually, it's kind of interesting that y ends up being this 84.015 feet as well. So there are my dimensions, and that's really what it asked for. If it did ask me for the maximum area, just another nice little trick, that would be the area when r is 84.015, and the area function is still in y1. So there's nice little tricks here. You could say, hey, I'm just going to take my y1 and plug in that a value of 84.015 for r. That's going to yield the maximum area, and here is that area. That would be the maximum area, 25,204, etc., square feet. But they didn't really ask for that here, so I don't care. But there are a lot of problems where they do ask, for whatever that main function is, the maximum or minimum value. So just nice to know little tricks with using your calculator, making it an extension of yourself. So there we go, kids. Optimization, a tricky unit, lots of word problems, lots of little things like this. So hang in there, keep working hard, and as always, ask if you have any questions.